Hello everyone. We will carry our discussion forward from where we had stopped in the previous class. In the previous class, I had introduced you to linear operators. A linear operator, some of the properties of a linear operator, and then some basic definitions of such an operator. What is a self-adjoint operator, or a Hermitian operator, or anti-Hermitian operator, and unitary operator. In today's class, we will be looking at basis expansions of linear operators. So before that, I'll introduce it to you the concept of a commutator. In general, the operator multiplication need not be commutative. That is, if I have two operators A, B, and these two operators, they operate on some vector, let's say, then the order in which they operate, that is going to matter. Okay, so it does not matter. If you first operate this operator B and then you operate the operator A, and in another case, let's say you operate operator A and then you operate operator B, the result need not be the same. Okay, so in general, operator multiplication need not be commutative. They can be commutative in under certain circumstances, but in general they need not be commutative. So in case they are commutative, then what will happen is AB will be equal to BA. Then we say that the two operators, they are said to commute. Now, how well do two operators do they commute? The degree of the extent to which they commute, that can be quantified by a certain object called as a commutator bracket. Okay, you would have probably learned this in your undergraduate course in quantum mechanics. So commutator operator, okay, so this is defined as, we put inside the bracket, we put AB, then that is defined as first you operate B and then you operate A, then first you operate A and then you operate B, then the difference between these two results, that is known as the commutator bracket or the commutator operator. So if two operators they commute, that means the order does not matter, then their commutator bracket will be equal to 0. The commutator bracket, more formally what I should be saying is, the commutator bracket, when it is applied on a vector, if the result is 0, then we say that the two operators they commute. So an example, suppose in a system of units such that h cross you take it as 1 and p equal to minus I d by dx, then xp is a commutator. Then it can be shown that xp is equal to I and xp square is equal to twice ip. So these are some elementary results from your quantum mechanics course. Okay. Then these following arithmetic manipulations can also be carried out on commutators. Okay, so you change the order of the commutator a comma b, then that is the same as minus of b comma a. And if suppose I have one of the operators, it's a combination of two operators a comma b plus c, then you can distribute them, so a comma b plus a comma c. And then if I multiply a commutator bracket with some constant alpha, then that is the same as multiplying alpha with either of the two operators. Either you multiply alpha with a or you multiply alpha with b. Okay, so now coming to basis expansion of operators. So let's say I have Hilbert space which is spanned by an orthonormal basis set. Now the moment I say it's a Hilbert space, that means we understand that this basis set, there is a scalar product which is defined. Okay, that's the criteria for a Hilbert space, for a vector space to become a Hilbert space. So there it happens to be a scalar product which is already defined, so that is understood. So let's consider a Hilbert space which is spanned by an orthonormal basis set phi mu. Mu is the index that we are using here. Then suppose A is a linear operator on the Hilbert space. Okay, so if A is a linear operator on the Hilbert space, then there exists two members in the Hilbert space. Okay, so let us say I have, this is my entire Hilbert space. Okay, this is my entire Hilbert space, and A is an operator which is defined on this Hilbert space. Then there exists two members, so you take one member. Okay, let's say this member is psi. Then if you operate on this member psi, if you operate A, it will take you to another member. If you operate A on psi, it will take you to another member. That member is your chi. So that's what we mean. So there exists two members in this Hilbert space, and these two members are chi and psi. Okay. So since A is a linear operator okay, and any member of the basis. Now this will be spanned by a basis. That's what we said, that this Hilbert space is spanned by a basis. The basis is phi mu, that's the basis, and phi is also a member, okay, any member. So if phi mu is also a member, so that means any phi mu, if I take any phi mu, this is also a member. So you can operate, because A is defined, it's a linear operator which is defined on the entire Hilbert space. So A operates on any member of this Hilbert space. So if phi, this set of basis vectors phi mu, if this is a basis vector for this Hilbert space, then A can operate on this phi mu as well. Okay, so A can operate on phi mu as well. So I will operate A on phi mu. Once I operate A on phi mu, the next thing that we know is any operator, if you operate on this, let's say I operate this A on phi mu, okay, I operate A on phi mu, it gives me some other element, okay, some other element, let's say something like theta mu, okay, just an example, theta mu. Now theta mu is a vector, right? Theta mu is a vector. We know that any vector in the Hilbert space can be expanded by using the basis vectors. So that means this theta mu can be expanded. This theta mu can also be expanded using this set of basis vectors. So whatever is the result, so I'm not writing it explicitly as theta mu. This theta mu is nothing but A operating on phi mu. So this can be written as a linear expansion. So something into phi 1 plus something else into phi 2 and so on. Okay, so that's what we're writing over here. Okay, so when A operates on phi mu, the whatever result you get, that you can expand it using the basis phi nu itself. Here I'm using nu just to distinguish between this index and this index. So that's why I'm using nu here. So how do you get these coefficients? How do you get these coefficients? Remember in the previous class I told you about orthogonal expansion using a basis. So if I have a, let's say an element, okay, let's say an element of this vector space F, this element of this vector space F, it can be expanded as AI phi I. Okay, and how do you get this AIs? We get this AIs simply by taking the scalar product of these phi i's with this function f. So how do I get these coefficients? How do I get these coefficients? By the same logic here. By the same logic over here, we get these coefficients as by taking the scalar product of phi mu with this function on the left hand side, which is a phi nu. Okay, scalar product of phi nu with a phi mu. Now this one is written in a more common form. It's written like this. We put a bar in between a and phi mu also. Both are exactly the same thing. It means that a operates on phi mu. Okay, so instead of writing it like this, just to maintain the symmetry, we put a bar, okay, on either side of a. Let me erase this. Okay, so this is what we have. So we have chi, which is equal to a operating on psi, and we have a phi mu is equal to a nu mu phi nu. Okay, so now these two members, chi and psi, because they are members, they are also members of the same Hilbert space. Chi and psi, they are members of the Hilbert space. So these two can be expanded individually. So we might as well expand this as in terms of this nu, right? So we put some coefficients b nu. We can expand it like this. Similarly, this can also be expanded. Okay, so some phi mu and some other coefficients c mu. So that's what we have done over here as well as here. So chi and psi we are expanding in terms of the same basis, whichever is the basis of the same Hilbert space. So using that, we can expand it like this. So now let us operate this operator on this psi, because that's what we are doing over here. Let's now operate this operator a on psi. Okay, so we operate a on psi. So a, now this psi, we are expanding this in terms of the basis. So a is equal to, psi is equal to c nu phi mu, c mu phi mu, and this c mu, I could take this over here because it's a constant, one of the properties of linear operators. You could just take this constant outside. So a now operates directly on phi mu. And when A operates on phi mu, the result is this. Okay, using this equation number 2. So this gives us A nu mu phi nu. Okay, so we have A psi is equal to, I can just collect this, A nu mu and C mu, and then we have phi nu. Right. So now what is this A psi? A psi is equal to chi. So we replace, substitute chi over here. So chi is equal to this quantity. So let's call this equation number 6. So we have chi, we have two expressions. First is, we are writing chi as a linear expansion of the basis, and then we found chi in terms of these coefficients, the coefficients C mu, which are the coefficients of psi, not chi, these are the coefficients of psi. So you can see what's happening here. On this side we have the expansion, we have an expansion of chi with respect to psi itself, having its own coefficients, but on the right hand side we are using the coefficients of some other function. That other function is psi. Okay, so with that we are able to expand chi. So we have these two. So equating both sides, we get that this left hand side must be equal to this on the right hand side, and this function is arbitrary and it's the same. So it means B nu is equal to A nu mu C mu. So that's what we have here. Now this is basically a matrix multiplication, because what are these? We have seen this is a column matrix, this is also a column matrix, and this is a n cross n matrix. Okay, so this is basically a matrix multiplication. So if this one represents a n cross 1, if this one is an n cross 1, then this also is a n cross 1 matrix, and then this must be an n cross n matrix, and we already saw that operators, you can write it like this. Okay, so we can define this way. We define a matrix C, B and A. So what does C represent? What does C represent? C represents this, C represents this vector psi. Okay, and B represents the vector chi. Whatever is on the B is on the left hand side. B is on the left hand side. So the vector which is on the left hand side, which is chi. So B represents the one on the left hand side, and A nu mu, these are the elements of the matrix which correspond to the operator A. Okay, so this is basically an operator, and this is basically a matrix multiplication equation. So therefore the operator equation, it becomes, this was the original operator equation, that is when the linear operator A operates on psi, it gives us a vector chi. Instead of writing it like this, you take the coefficients, and take these coefficients and take the elements of this and then construct matrices, and you can write this as a matrix equation. So the information in this equation and the information in this equation, both are exactly the same. Okay, so using this we can actually do a problem. So this is the problem is, so let's say we consider a Hilbert space of quadratic functions. Okay, we have a Hilbert space of quadratic functions which is spanned by this basis, and this you can identify, these are the Legendre polynomials, the first three Legendre polynomials. You can see here this degree is 2, so that means any linear combination of these three will give us all quadratic functions. So suppose I define a linear operator like this, that is S multiplied, first you differentiate with respect to S, then you multiply with S. So we define a linear operator like this. Then we have to obtain the matrix representation of this. We have to obtain a matrix representation of this operator and use the matrix to obtain the result when the operator is applied on the following vectors. That is, what if I apply, what will happen? What will be the result when I apply this operator on this function? So what will happen is S, what will happen when I do S d by ds of psi? What will happen if I apply S d by ds when I apply this on sigma? What will happen? So this is what we need to find out. So here this relation is extremely useful, the orthogonality, the orthonormality condition for Legendre polynomials. So any two Legendre polynomials, okay, if I multiply them together and integrate from -1 to +1, then any two Legendre polynomials, they are going to be orthogonal, but they are not normalized. So how to normalize this? We can use this condition. So when you integrate from -1 to +1. So I can identify here that this is nothing but a scalar product. So you can see here this is nothing but the scalar product Pn Pm. Okay, the scalar product of these is nothing but twice delta Nm divided by twice n plus 1. So we can use this to solve this problem. So let's go ahead and do this. So okay, first let me grab this. Okay, so this is what we have. This is the problem that we have. So now we'd like to go ahead and solve this. So what we can do is we'll first make use of the orthonormality condition to find out the scalar products of these different members of this basis. Okay, what are the scalar products of these different members when they are applied on each other? Okay, so let's go ahead and do that. So first what we will do is we'll find out P0, P1 and P2. So our basis here. So the basis here, the basis is P0, P1 and P2. This is our basis. So now we'd like to find out what happens when I take the scalar product of each of these. So what will be P0, P0. So this is what we want to find out. And like I had mentioned here, this is nothing but Pn and Pm. Okay, so all I need to do is just use this formula. Okay, the right hand side. So this is equal to. So this is equal to, we have twice delta. Okay, this is n and this is m. N is 0, m is also 0. So twice delta 0 0 divided by 2 times 0 plus 1 twice delta 0 0. This is going to be equal to 1. So 2 times 1 divided by 2 times 0 is 0, and what is left behind is 1. So this is equal to 2. In a similar way, we can find out P1 P1. Okay, I'll leave this to you. This will find out to be equal to 2 by 3, and likewise P2 P2, this will be equal to 2 by 5. Okay, please work this out. P0 P1, P0 P2, P1 P2, all of these will be obviously 0 because they are orthogonal. Okay, so let me write those here. P0 P1, P0 P2 and P1 P2. These will be all zeros. So now we need to construct an orthonormal basis set. Okay, because P0 P1 they are not normalized. They are not normalized. So therefore the orthonormal basis set is, so let's construct, how we are going to construct is this. From P0 we will construct phi 0. From P1 we will construct phi 1, and from P2 we will construct phi 2. Okay, so this is how we are going to construct. So over here this one will be orthonormal. These will be orthonormal. Okay, but these are orthogonal but not normalized. This we already know, as we can see from here. Okay, the result, this is not 1. So they are orthogonal, but they are not normalized. They are not normalized. Okay, so how do we go about doing that? That is very easy. We'll just have to divide this P0 with its own norm. Okay, so for instance, let's say I want to find out phi 0. if I want to find out phi 0, then all I need to do is I have to take P0 and I have to divide P0 with the norm of P0. Okay, and this we already know. What is the norm? Norm is just the and this norm, it is nothing but the scalar product of the self scalar product taken under the root. Okay, so we can do the same thing for the others as well. Okay, we can do the same thing for the others as well. For phi 1 in a similar way, for phi 1 also in a similar way. So phi 1, P1 divided by norm 1, P1 divided by root over self scalar product of P1. Likewise for phi 2 as well. Okay, so this is going to turn out to be equal to, you can work this out for yourself. This is going to turn out to be equal to 1 by 1 divided by root over 2. Divided by root over 2. Then this one is going to turn out to be root over 3 by 2 root over 3 by 2 s, and the last one, it's going to turn out to be root over 5 by 2 root 2, root over 5 divided by 2 root 2. Root 2 times 3s square minus 1. So I'll leave this to you to verify, okay, for yourself. Okay, so we might as well write it like this. From here we can just, if you want to switch from this one set of functions to another set of functions, so we can write down this P0, you can say this P0 of s is equal to root over 2 times phi 0 of s. In a similar way, P1 of s is equal to root over 2 by 3 into phi 1 of s. And finally, from here, this implies that P2 of s is equal to root over 2 by 5 root over 2 by 5 of phi 2 of s. Okay, so now let's consider the operator. The operator was that is, this is the operator A S d by ds. A is equal to S d by ds. So the operator is A, which is S d by ds. Okay, so now we know that is from these expressions, because we are able to write this P0, P1, P2 in terms of, oh sorry, my mistake, this should have been phi 2, not phi s. P0, P1, P2 we are able to write in terms of phi 0, phi 1 and phi 2. So we can actually express this 1 s and s square. Okay, so we know that or rather I think we can do this at a later stage. That's the second part of the question. Let's just proceed and find out the coefficients. Okay, let's do that first. So we want to find out the elements of the operator matrix are, okay, so how do you get the elements of the operator matrix? So we have A, let's say nu mu, this is equal to A nu mu, this is equal to, we just saw in the slides, this is equal to phi nu A phi mu. Okay, basically these. Nope, I think it's here. Here, A nu mu is equal to phi nu A phi mu. Going back to this, so therefore we can use this to find out the coefficients. Okay, so what are the coefficients? This is the n cross n matrix. So A, how will A look like? Okay, the matrix A, how will it look like? So we'll have a A0 0. Okay, so we'll have A0 0, then A01, A02, then A10, A11, A12, A20, A21, A22. Okay, so this is how the matrix A is going to look like. It's supposed to be an n cross n matrix. The dimensionality is 3 because our basis has got 3 elements, so the dimensionality is 3. So n is equal to 3, so it must be a 3 cross 3 matrix like this. So we need to calculate, we need to find out each of these each of these individual elements. So first let's find out A00. So we can use this formula. So let's find out A00. So what will A00 be? A00 will simply be equal to phi 0 A phi 0. This mu and nu will simply become 0. Okay, so this is what we have. So now just apply this. So what is the definition of this scalar product? The definition of the scalar product is of course, so -1 to integration -1 to +1, then the first function, okay, then followed by operator A operating on the second function. So this will be equal to integration from -1 to +1. The first function is phi 0. Phi 0 is 1 by square root of 2. Okay, phi 0 is 1 by square root of 2. Then A is equal to S into d by ds. A is equal to S into d by ds, and again phi 0 is 1 by square root of 2 times ds. Now this will obviously be 0 because this operator, differentiation operator, operates on a constant, and the result is going to be 0. So a00, that is going to be 0. So we will have a 0 over here. Next, a01. A01, how do you find out? Again, 50 a 51, 50 a 51. So now same way as before, integration -1 to +1, 1 by root over 2, that's a 50. Then the operator, which is s into d by ds, operating on 51. And what is 51? What is 51? 51 is root 3 by 2. 51 is root 3 by 2 into s. So this is going to operate on this function, root 3 by 2 into s ds. So as a result of this, we'll get a root 3 by 2 outside, root 3 by, yeah, because this root 2 and this root 2, that is going to give us 2. So we'll get outside root over 3 divided by 2, then integration from -1 to +1, and what is left behind is, okay, d by ds operating on s, that is going to give us 1. So we have s into ds. And when you work this out, okay, when you integrate this is going to give us 0. So you'll get a 0 here. So a01 is also 0. a01 is also 0. Okay, next a02. Let's find out a02. a02, this will be equal to 50 a 52. Same way as before, so we'll have integration from -1 to +1. 50 is 1 by root 2. 50 is 1 by root 2 s into d by ds, and then we have phi 2. Okay, so you can write down phi 2. So phi 2 is, we've already found out, phi 2 is root 5 by 2 root 2, 3s squared minus 1. So we write this down here, root 5 divided by 2 root 2 root 5 by 2 root 2 times 3s squared minus 1 times ds. Okay, so when you differentiate this, differentiation of this d by ds, it will differentiate only the first term, because the second term is anyway constant. So that differentiation is going to give us 0. So when you do that, you will get, I'll just write this down straight away. So we'll get a root over 5. Divided by 2 multiplied by root 2 into root 2, which will give us another 2. So 2 times 2 just give us 4. So root over 5 by 4. Then we have -1 till +1. Then we have an s here. And then differentiation, d by ds of 3s square. d by ds of 3s square is 6s into ds. So this is going to give us 6s square. It's going to give us 6s square into ds. 6s square into ds. And when you integrate this and find out the result you will get it to be equal to root over 5 by 2 into 1 minus -1, which is going to give us root over 5. So a02 is going to be root over 5. Okay, so a10, likewise you can find out A10 will turn out to be equal to, I'll give you the values. You can work this out for yourself. In a similar way, you can find out for each and every one. So A10 will turn out to be equal to 0 again. A10 will turn out to be 0. A11, the value is going to turn out to be 1. A11 will turn out to be 1. Likewise, if you calculate, find out A12 coefficient. This one's value will again be 0. Then A20 will also be 0. A20 is 0. A21 will also turn out to be 0. And finally, A22 is going to be non-zero, and this result will be 2. So this is how the matrix is going to look like. Okay, 0 0 root 5, 0 1 0 0 0 root 2. So this represents, okay, so I leave this to you. Okay, the calculation part, the calculating the other coefficients, you proceed in a similar way, and finally we will get this one. Okay, and likewise, and likewise. So therefore A is equal to this, and this represents the operator, the linear operator, A, which is equal to S into d by ds, the linear operator, this. Okay, so this is what we have. Now let's go to find out this the problems that we have been asked to do. The first problem that we are asked to do is this one. We apply A on the psi, and what is psi? 3s square plus 5s plus 2. Okay, so now let's do this part. Okay, so now given we have psi, and the psi is 3s square plus 5s plus 2 plus 5s plus 2. Okay, so 3s square plus 5s plus 2. I hope I'm right. 3s square plus 5s plus 2. Okay, so now we need to express this one. Okay, we need to apply this operator A on this psi. Okay, and then we have to see what result do we get. Okay, so now we need here s square and 2, right? All three we need, s square into 2. So this can be written. So now let us just write down these 1 s and s square in terms of phi 0, phi 1 and phi 2. 1 s and s square in terms of phi 1, phi 0 and phi 2. Okay, so this from here. So I'm going to use this result. Drag it down, 3 square minus 1. I have to include an extra 3 square minus 1. So this is what we have. 3 square minus 1. Okay, so these are your phi 0, phi 1 and phi 2. Okay, I really don't need these. Let me get rid of these. So we have this is our phi 1 and this is our phi 2. Okay, so hence we can write 1, right? What is 1? 1 is nothing but your P0, right? 1 is nothing but your P0. 1 is nothing but your P0. 1 can be simply written as root 2 times, 1 can be written as root 2 times phi 0, right? You just take the root 2 this side, so right, this side we get 1. Likewise, what about s? S is your p1, right? S is your p1, and we can write s as root over 2 by 3, root over 2 by 3 into phi 1. And finally, you can check, we did something similar when we did that Legendre polynomials problem. S square can be written as root over, s square can be written as root over 2, or we can rather use this one. I had arrived at this result earlier. S square can be written as p0 by 3 plus 2 by 3 into p2. So s square can be written like this. If you evaluate, you'll get s square, and this is equal to root over root 2 by 3 into phi naught plus 2 root 2 divided by 3 root 5 into phi 2. Okay, so this is what we have. So now we can use this and express this one. Okay, so using these in psi, we can use these in psi. So what is psi? Psi is this. Psi is basically this. All we need to do is just substitute them. Psi is this. So 2 into 1, this is 2 into 1. So 2 into 1, we'll just get a 2 root 2 into phi naught. Okay. Then we have 5s. Okay, 5s. And what is s? S is 2 root 3 phi 1. S is 2 root 3 phi 1. So into 5 into 2 root 3 into phi 1. Okay. Then we have s square. We have s square, and what is s square? S square is this. So we have 3s square. Okay, so 3 times this entire thing. Three times this entire thing. And this. Okay, so now what we need to do is we can just combine all this phi 0, phi 1, phi 2 terms together, and this is going to give us psi to be equal to 2 root 2 into, you can verify for yourself, this is going to give us 2 times root 2 times phi naught, then plus 5 root 2 by 3, 5 root over 2 by 3, 5 root over 2 by 3 into phi 1, and lastly this will be 4 root 2 divided by root 5 into phi 2. So this is what we have. Okay, and then you can see here, these are the coefficients, right? Because if you can see, this is nothing but your let's say c mu phi mu, right? Over here mu goes as 0, 1 and 2. So these are your c coefficients, this and this is your c coefficients. And if you recall, here we represent this in terms of c. Okay, column, this c represents this psi. Okay, so we represent this c. So you take these three coefficients and create a column matrix that is going to represent c. So therefore this column matrix c, which we write as this, The first element will be 2 root 2. The first element will be 2 root 2. The second element will be 5 root over 2 by 3. And the third element is 4 root 2 by root over 5. So this is your column vector, and we have the matrix A here already. Okay. So remember, what are we trying to do? We are trying to find out here that what will happen if A is applied on psi. This is what we want to find out, right? So equivalently, what can we do? Okay. So let's say this is equal to B. This is equal to, let's say, chi. This is chi. So what we do is we'll make this change. So this one will replace it with some column matrix B. This one will we replace it with the column vector C. This is B and this is C, and this A I'll replace it with the matrix A. So this is what we have. We already know what is A and B, A and C. We already know this and we know this. So we just need to multiply these two, and that is going to give us B. So let's go ahead and do that. So here, so therefore this column matrix B that we are looking for, this column matrix B is equal to A, C, and we already have A. Let's grab A from here. What is A? A is this. A is this matrix. A is this matrix, and C is this matrix. This column vector is your matrix C. So this is just C. So now all that you require is just do a matrix multiplication. So when you do a matrix multiplication, this is going to give us, you can work this out for yourself. This matrix multiplication is going to give us first element will be equal to 2 root 2. Second element will be equal to 5 root over 2 by 3, and the third element will be equal to 4 root 2 by 5. 4 root 2 by 5. Okay, so this is your B. This is B. Okay, so this is the result. So what does that imply? You see here, B represents this matrix B represents the vector chi. Okay, vector chi. So which means, so therefore, what is this chi? Chi is equal to this first coefficient, which is 2 root 2 times phi 0. Next coefficient, which is 5 root over 2 by 3 into phi 1, and the last coefficient, which is 4 root 2 by 5 into phi 2. So this is your chi. Now if you expand this phi 0, phi 1 and phi 2, if you expand phi 0, phi 1 and phi 2, okay, if you expand phi 0, phi 1 and phi 2, you will find, okay, expand phi 0, phi 1 and phi 2, you will get chi, you will get the expression for chi, and it will turn out to be very simple actually. The expression chi, that is going to be 6x square plus 5s. That's what you will get, because you can try this out for yourself. So this is what is meant by, this is how you can use the basis expansion of the operators to quickly operate a vector, to operate a linear operator on vectors, and we can represent this process equivalently by using matrix operators, using a matrix equation by matrix representations. Okay, so yeah, so this is the example. So I suggest you try the rest of the problem which I had left out. You can try this out on your own. In the next class, we will look at self-adjoint operators. So let me stop here for the time being. In case you have any queries, please feel free to text me or send them by email to me. Okay, thank you.